Hello, I'm going to make a program to make a playback for a WAVE file, okay? And this is the hardware setting that now I'm using. The OCR0A and OCR0B, that means the PWM output is fitted into, there's a 3.9 kilo ohm resistor and a 1.5 nanofarad capacitor, and actually here it forms a low pass filter, and its cutoff frequency is at 27 kilohertz. And then this 3.9 kilo ohm, 3.9 kilo ohm, and this 1.2 kilo ohm. Those resistors form a potential divider, and I get output around just a little bit below 0.7 volt, and they are fed into the PC sound card line in, and I'll do the playback, and the sound comes from the PC speaker because I feed the signal into the PC sound card, okay? And let's see what I'm going to do. I have to make a new folder. Yep. I already make it. Yep. Okay. I make a new folder called a PWM 8-bit part 1. Okay. Then I copy all files from the last program. It's from the PWM folder. Is here. Okay. Okay, and I have to delete something first. Okay, done. Okay, then I have to actuate to use the AVR Stidio. Yep, AVR Stidio. And then new project. Okay, that's correct. Okay, next I select the microcontroller. Okay, I add the source file, I add the header file. Okay, then I have to set the crystal frequency 16 MHz. Okay, that's good. Then I have to make some change in the main.c. Okay. The first thing here is that I have to change the buffer size. I change it to 512. Okay. Then here, the size of wave data. Okay. It should be double word, not unsighted integer here. Okay. Then the frequency should be unsighted integer, and I add a variable called RI. This is the read index. That means the location where I read those data bytes from the buffer. Read from the buffer. The location. Okay. Then here I add another variable called K that I use in the interrupt routine. Okay. Then I need an interrupt routine and interrupt setting. Okay. I need those two things. So I just make a copy of them and I put it here. Okay, that's good. Then in the main function here, okay, I have to remove this thing, those settings that I used in the last program to generate a 267 Hz square wave, but I don't need it now, so I just delete it, remove it. Okay. Yep. And I need those cooks to the pay function. Here, okay. I make a copy of them. Yep, and I just put it before the error exit. Okay, I put it here, and yet I have to make some change. Yeah, the stop pay. I have to make a change here. Go to stop pay. Okay. I think that's alright, so let's compile that. Okay, that's good. So now I upload the program to the microcontroller. Okay. Okay, content, you go to file. Okay, I got it. Okay, no, this one here and this one here. Okay. Okay, I change it here. When I select the PC line in, I will lose the microphone input. Okay, so I lost my sound. Okay, now I change it to the PC line in here. Okay, hello. Okay, so here I insert the SD card. Okay, do a playback of changing partner. Okay, now I change the input to PC line in. Hello. Okay, I got a sound again. I think that you will feel the playback is a little bit noisy, and I'm going to make it very good in the next video. Now it is noisy. This is quite normal because there are some data corruption. That means the rate that data is read in from the SD card and the rate that data is consumed by the interrupt routine here is not going well. So there is data corruption, and still I would like you to notice that the playback is a little bit faster than normal, and actually this is just what I want, because that means the microcontroller is fast enough to do the normal payback, it can be very good. Okay, but still I want to make it run faster, so I will make some change here. Yes, here. I will make some change to the part here, that receiver part of the sector. Okay, I will change this. Okay, it will make the read in from the SD card a little bit faster. Okay. Hello. Okay, let's take a listen. Okay, now I build it again. Okay, it's done. Okay, now I turn it off. Okay, I take off. I take the SD card from the slot. Okay, I take out the SD card. Then I upload the program. Hello. Okay. And now I insert the SD card. I do the payback. Yeah. Let's just make it like that. Okay. Hello. Okay, I still got my sound. Okay, I think that you can hear the payback is just faster than normal. Okay, but still, let me make some more example. Okay. Okay, now you see the error. Okay, the read-in is just too fast and faster than the payback consume the data. So there is data corruption, and it sounds no good. But in the next video, it will be very good. Okay, and still I want to explain something else here. In this interrupt routine, when the interrupt routine fire up, if at this time a data byte is received from the SPI interface, that what will be the result? It simply would be lost this data byte, because the interrupt is running. So how to prevent this? I just slow down the SPI clock rate, so I change it to 5 V here, especially the 3. So it changed the SPI clock rate to CPU frequency by 64. Okay. After slow it down, then it has to handle the data byte. Okay, to handle the payback. If this is a 8-bit file, then the data byte is for both left channel and right channel. And for 8-bit, the format is just unsighted character, so there is no need to make any change or adjustment. I just push this value to OCR0A and OCR0B. That means I push it to left channel and right channel. If this is 8-bit but stereo, then the first data byte is for the left channel, so I push it to OCR0A. And the next data byte is for the right channel, so I put it to OCR0B. If the file is 16-bit, then I have to make some amendment. Okay, the wave file, 16-bit wave file, is using cited integer format. That means its variation range is from -32768 to positive 32767. But we're going to handle positive value here, so if the data byte read in varies from negative to positive, so what are we going to do? We just shift it up. So here I add 128 to the higher byte. Effectively, it changed the value. It will change the variation range from 0 to 65536. Okay, 35. Okay, it will effectively change it from cited integer to unsighted integer. Okay, so if it is a mono 16-bit, then the first byte is the lower byte, so just fit it to OCR0A and OCR0B. What is it doing here? Because in the coming videos I will make the output become 16-bit resolution, and I will use a timer 0 for the lower byte, so write the value to OCR0A and 0B. Okay, and then the higher byte, I have to correct it by adding 128 to it, and then I write it to OCR0A and OCR0B. Okay, if this is stereo 16-bit, then the first byte is the lower byte, so put it to OCR0A, and the next byte is the higher byte of the left channel, so I add 128 to it. This is a hex X0. Okay, after this correction, I write the value to OCR0A. Okay, and then still the next byte is the lower byte for the right channel, so I write it to OCR0B, and then the next byte and add a 128 to it and write it to OCR1B. Okay, after those things that I have to take care about the value Ri here. Actually, I can do it like this. If yes, I can do it like this. But if I compare those two things, they will give the same effect, they will give the same result. But obviously, this one works faster. So I just delete this one. And after all those things, I restore the SPI clock rate, and this is all the trick that I use here. It makes a successful payback, but at a faster rate. Okay, that's all for this video. See you next time.